Okay, cool. Yeah. So that worked, and yeah, he told me it's in the newest version, and so I just upgraded to the newest version. Not terribly hard. You just go to here and you just run the script again if you installed it manually, right? I installed my Babashka under /bin under my home directory, so I just replaced temp with bin, um, and that's it. Yeah. So that will get you the newer version of Babashka, and when we do so, you can see I just ran it again, and yeah, we're getting past the closure.zip thing. So we do now have closure.zip, and that's great. Cool. So that was easy. Let me just thank them online. I'm going to just mention this project itself, which I think I called CTCI. Oh my gosh. All right, so let's see. Back to 4.3. All right, so now we're really actually starting the problem. Maybe I should restart the vid. Now, I think it's good to even include the incredibly, like me, flailing around parts, right? So that people know that that's totally normal. All right, 4.3, list of depths. So, it's really dark today. It's like yeah, it's very overcast. So that's good. Today's a bike ride day, and I guess it's a short enough problem that we can just write down the problem. Okay. List of depths. All right. Given a sorted, increasing order array with unique integer elements, write an algorithm to create a binary search tree with minimal height. Wait, that's not right. I switch. I'm reading the wrong one. Given a binary tree, design an algorithm which creates a linked list of all the nodes at each depth. Okay. If that's pretty much it. Yeah. So all right, that's it. said NS, but Alright, so we can get rid of this because we don't need to bring anything in. And we can rename this to list of depths. It's going to take a, oops, it's going to take a tree, and we don't know what it's going to do yet. But then okay. So, you know, a tree might be, okay, what about for the empty tree, right, with no children? Well, then we might expect to get the empty list, right? What about the tree with, actually, no, that's not what we would expect. We expect to get this. I guess. This is going to be a very... I'm going to, rather than actually do that, I'm going to specify them using identifiers. So what if you pass in nil, as in there is no tree? Then it should truly return the empty list, or it should return nil. It should return the empty list. What if you pass in a thing with an ID of 1, right? Then it should pass in 1. And it should be the grouping 1, right? Because, oops. What if you pass in a thing with ID 1 and children? Or maybe we should do just left and right this time. Let's give that a no, let's do children. Children of ID 2, right? Then you should be 1, and then you should have another one that says 2. What about ID 2 and ID 3? 1, you should have 2 and 3, right? Now we can have the tree can be in any form, so like what about 1 and 3? Well, that really doesn't make a difference. What about, well, just do a conventional one. So this is still a perfect, I think is what they call it, tree. A complete tree is what I meant to say. Yeah, complete, full, and perfect. Okay. Complete just means you're basically you're fully filled, other than your last row with it, which is filled left to right. Full means everybody has 0 or 2 children, and perfect means that you're basically a perfect mirror of yourself as a tree. Yeah, perfect means you can be split. Doesn't mean mirror, because you can also be... Oh, wait. Does perfect have to have an odd count? Yeah, I think a perfect binary tree has to have an odd number of nodes, right? Anyway, so All right, and ID1 children. Okay, so what about where this guy has a child? He's got a child of one. Sorry, a ID of 4, right? So what should this guy return? He should be 1, 2, 3, and there should be a 4, right? But this should also work. You should have an ID of 4. Right, same thing, ultimately. Now I'm kind of feeling like let's do this. That sucks. Oh well. Okay, so I mean we kind of know one thing, which is since it's a binary tree, the first element could have up to 1 element, the second element could have up to 2 elements, the third grouping, I mean to say, could have 4, the fourth could have 8, onward and onward. But it can be any way you want it to be. It could also just be a linked list. Let's do that. Alright, so ID1 contains ID2, contains ID3, whoops, contains ID3, contains ID4. Why do I feel like I'm missing something here? ID1 contains ID2, contains ID3, contains ID4. So I think I'm saying that that should be I'm just saying that should be 1, 2, 3, 4, right? That's a valid tree too. Or as well, I should say. And I forgot to actually put the result here, but it should be identical to this one. I feel like when you do this, you should just start doing spaces between things. This is too complicated. Too difficult to parse. Okay. 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 The map bill starting with ID contains 5 forms. Map littlest must contain an even number of forms. Well, okay. Only 27. So I screw that up. ID1, ID2 contains children, right? ID3 contains children. ID1. Ah. Okay, so everybody fails. That's good. All right. So let's just start with the basics, right? And let's start even simpler than that. List of defs. All right. So if you're if you are all right, if you're so I guess the first thing we need to ask is, are you a node or not? And I guess we'd ask that question by just saying, are you a map, right? And if you are a map, we're going to put you into a zipper. But if you're not a map, we're going to just return nil, right? So when you're a map, we're going to put you into a zipper. We're going to do something. So this should already pass the first one, right? Because what we're passing here is not a map. Why is it not passing? List of depths, map, tree. Oh, no, it should return nil. Yeah, okay. But when you are a map, we're going to do zip/zipper on you. And I've totally forgotten how to do this. All right, so let's go look at zipper. I don't even remember what I once read about, where I even read what I read about zippers, but so this is, I feel, not necessarily the best place to learn about zippers, but so what is a zipper? A zipper is three functions and one actual data structure, where the first function is given a node returns true if it can have children, even if it currently doesn't. So what allows you to have children? There is no limit to you having children. Anybody can have children. Blah. Anybody can have children. So I think that would be, for us, like as long as you're a map, you can have children because you can just add them into children. Well, what do they mean by can have children? Does that mean like I have space to have additional children? Because if I'm a binary tree, I can't have children if I already have two nodes, right? I mean, I can have children. I do have children. But can I have additional children? Do you mean can I have children, as in more children? Or do I mean, is it possible for this thing to have children? Let's look at the example. I think it's the question of, can you have children? Period. And so they're saying like a vector can have children because it's a collection type. And so we can just keep adding children into it. But a number, right, cannot have children because it is not a collection type and we cannot put additional things into it. So I guess you can have children if you're a map is what it sounds like, kind of. Right, which we kind of already affirmed here. Next question is a function that given a branch node returns a sequence of its children. Okay, so this gives me the list of existent children on a branch node. Okay, so that's just the keyword children. Okay. Make node is a function that, given an existing node and a sequence of children, returns a new branch node with the supplied children root. Oh, root is the root node. Make node is a function that, given an existing node and a sequence of children, returns a new branch node with the supplied children. I guess that's really easy. It's just a function that says a branch node. So what did they use for theirs, for instance? They just use seek. So doesn't this technically... Oh no, this is the second one. This is just give me the children. This is the one. Existing node and a sequence of children. Returns a new branch with the supplied children. But if that's a sequence of children, doesn't this convert my... How come this doesn't convert into a sequence? And how come it's still a list? Okay, so this is just making the data structure. We're going down. Yeah, see, it's converting things into sequences from vectors. So, okay, I just want to make sure that that would be happening. Okay. Anyway, but we can stay maps the entire way. So all we're going to do is take a node and a children, and we're just going to say associate into, just taking a map and a children, associate into the map the children of children. And the final thing is just take the tree, right? And so that's our zip. And ours is technically not a binary tree zipper. It's actually a you can, if you walk around on this thing, you can add more than just two children. You can also we could make it so that it always has the children is always either 0 or 2 elements, or it's always 2 elements, but some of the elements might be nil. Or we could do it the way we've done it here, where you don't specify the children you don't have as nil. You just don't include them. Oh, you know what? I think that's what I actually meant to do down here. No, this is a linked list example, but this one is. Well, anyway, I think this is another example where it's like, I guess there's no real way to specify that. I mean, we don't have, I guess we don't really have the notion of left and right node. We just have your children. I mean, your left one is implicitly the first one, your right one is implicitly the second one. But, like, is it right to say nil ID4 to literally indicate that I want ID4 to be hanging out on the right side, you know? Let's not deal with that right now. But, anyway, I think that's a tree zipper. So, given that we have that, yeah, so it's just returning the zip form of the thing. But what we need to do is basically walk across. I mean, there's a pre-walk and a post-walk in here, I believe, too. Oh, you know, let's look in the actual. Where's pre-walk and post-walk? Oh, it's under closure.walk. Interesting. Okay. I wonder if we have that. We do appear to. Okay. Demonstrates behavior pre-walk by printing each form as it is walked. Returns form. So how does this walk it? Well, it starts with the root. Well, not really. I mean, it starts at the highest level and walks through every O. So this isn't quite what we want, I don't think. Well, or is it? Because we could basically say, no, let's stick and zip. I'm pretty sure I can just take neck, or first of all, let's try just taking the node, right? Just to see what we see. So yeah, so now we got the original guy back, right? That's basically, we put it into a zipper and then we pulled it out of the zipper. But then, so that's cool. That's how we get the items. But the current item is focused on, the focus of the zipper is currently on the node, or on the root. But, and how do we get the next? Search child. Okay, all right. But then how do we we have this data structure, we kind of just want to get a list of all the nodes, right? Yeah, I think so. Um, okay, so we have the zipper. The Z. So I think we just want to call iterate zip slash node on Z while what is the last element going to be? How do we terminate? End. I'm actually just not sure. I don't think this is necessarily right. Well, let's see what we get. That is not what I expected. Iterate zip slash node Z take while zip slash end. Not expected. All right. Why is it? Just I think it's saying. Well, yeah, I mean it should take at least one, right? Wait, I said node, but I meant zip slash next. No, okay, let's just take out the take while. Well, now it'll never finish. Alright, so I think I got an infinite loop going here. Alright. Zip slash next, and take while zip slash end. Return true. It's not a depth first walk. I guess. Moves to the next lock in the hierarchy, depth first. When reaching the end, returns a distinguishing lock detectable by and if already at the end, stays there. Okay, interesting. So actually the end, if we take, because we're already at the end, it's not taking it. Huh, okay. Shoot. So what if I want the thing, I want to include the end, basically. Right? So I want to take all the items, including the end item, as a sequence. So I don't want take while, because that'll stop me before the end item. I mean, one way I could do this is just partition 2, 1, whatever, so that I can be like, well, if it's ever the case that the node is the same node, then we know we're at the end. And so that's the last one you take. But that's also got a take while issue. I want to take one more than the end. How do I do that? I mean, I haven't changed the tree at all. That doesn't really matter, but take while I'm at the end. I do actually think it would have been easier just to convert this tree into a graph and use our BFS thing, but that's okay. I think this was good to figure out how to use zip because it was something I kind of was hesitating to do because I wasn't sure how to do it, so that's fine. Zip next. So I think we're fine with zip next. There is no next. In fact, the first end is already, the first node is also the end. So, yeah, I don't really know how do you do that? How do you, it's like some sort of sequence processing thing. Include the one that is the predicate, rather than just running through the whole thing twice and something silly like that. Jeez, what is that noise? I'm gonna go look outside. It's just a poor homeless woman who's, admittedly, that's just how she vocalizes. She doesn't appear to be in any pain. She just makes that noise constantly as she, picks up cigarettes from the ground and stuff. Ugh. That's terrible. All right. Seeing more and more stuff like that since this shelter-in-place thing has gone into effect. Not that I blame the shelter-in-place at all. I'm just saying it is becoming worse. Okay. Well, there's zip and Iterate, zip next, Z. Chapter 4, problem 3, list of factors. Okay, what was it? Yeah. Focus. Alright, so I want something that actually kind of gives me. It's like Take a While, except I also want the thing that you failed on. Let's drop S4. I mean, distinct would actually logically work, right? Because, like I said, once you hit the end, it just keeps returning the end every single time. But the funny thing about that is you have an infinite sequence that it's having to process through at that point. So, group by, partition by, play shuffle. You know, I'm just not sure how to do that actually. Okay, so one thing I'm going to do is actually get my Clojurian's thing in here, so I can actually just ask questions on and have them answered, because that would be really nice. I think it also illustrates that the Clojure community is pretty friendly and helpful. Take while. Reduce take while partial 1000. Iterate inc 0. Could this help me? No. I want to just sequence through it once, but I don't. End isn't terribly useful, or I wish. I guess I can write my own predicate. No, I really. I mean, if I'm doing element-wise predicates, there's no way for me to know whether you're the first time this has showed up or the second time this has shown up. And so, geez, I mean, this seems just really dumb what I'm about to do, but it's the only thing I can think of right here. I feel like I'm doing something silly here. Take while, or it's not take while, but take while, or take up to. I don't know. On a sequence, right? I'm going to take the sequence. I'm going to partition. I gotta look this up. I want the one that basically duplicates stuff. In step collection. Okay, so I want 2, but I want my step size to be 1. Okay, yeah, I think that's what I want. 1. I think that works. And then what I want to do is I want to maybe we'll just call it take while inclusive. So partition to 1, and then what we want to do, we want to take while boom second on our predicate, right? And then before anyone's the wiser, we want to map on the first, right? Is that right? Is that... I'm forgetting something here, which is to map on the map on the vector of excess and cons of excess. Cons nil of excess? Let me think about that. So screw it, I need to write a function just to test this out. Wrong. Alright. Okay, so you are right. Let's just use the default predicate of. Oh, we'll include the predicate, sure. Alright, so if I specify even as the predicate and I say the numbers that I'm putting in are the empty list, it should return the empty list. Okay. If I'm saying even and the numbers I put in are 1, it should include 1 basically, even though that does not pass. No. So that's the desired goal. So let's just see what we got here. I got 1 nil, which, yeah, that's pretty much what I got. But now I want to... Oh, I'm just being dumb. That's not what I wanted at all. But I got this, right? Huh, that's not what I expected it to do. Oh, I put no padding, did I? Let's do nil, I guess. I don't know. Yeah. Oh, that's weird. It's... Wait, what the hell is padding? Oh, it's a sequence. Okay, 1 nil. Okay. And... So is that what I'm looking for? I'm not sure yet since I only have one test case here. But then I take while the second is on the predicate. That's weird. Matches the predicate. What's the problem here? Argument must be an integer. To who? To what? Oh, even. So I'm going to guess it got the nil. Fudge. So I need something that would never cause an explosion. That sucks. I mean, it's almost like I need to include what the padding would be, or the pad would be, because I need it to pass whatever predicate I would pass it. Boy, this just seems messed up. I think this isn't the right way to do this. I mean, we can make it generic without needing a predicate. What about index add or something like that? Am I just forgetting? or split at or something like that. The split at would take an index position, which means you've already had to read it. But I just want a split at that's more like a split with. Maybe that's what I want. There we go. I think that's actually all I want. Okay. Okay. So excess split with, and then we're going to take the predicate, and that's just going to return take and drop. Take excess and drop excess as a vector, and it's going to say split with predicate excess. Cool. And then all we're doing is kind of sucks, but we're going to just concat take excess with the first of the drop excess. I thought that would work. So I'm saying even. Well, yeah, there is no even. Does that make sense? And that is what I asked for, but now I realize that that returns you an item with a nil sequence even when you actually had no items. Weird. Does it make more sense to... I don't know, man. I don't know. Obviously this should work. Okay. What about 2, 1? That should technically return 2, 1. Yeah. Okay, I kind of think that's what I want, but it's a bit odd. Alright, so we got a thing that does that now, so I think now we can just say, alright, all nodes, and now we should be able to get, even when the node starts at, oh, you don't have anything testing. Oh, poop. Alright. Can I call take while plus 1 with 0 arguments? Okay. Well, it shouldn't be 0. It should definitely be 1, but, but yes, I agree that it should be with zip slash end. I would think that there's... oh. Well, son of a gun. Oh, I did this on mistake. Oh, and this shouldn't be here. This should be here. What was the purpose of it? Okay. So what do we got? Yeah, that's actually right, despite what it looks like. It's not really all nodes. The nodes are the realized value at that location. It's really all. Do you say all zippers? Is what you say? All locks is what it actually is, right? The locks. Okay. Okay. And then having done that, I want to convert every lock into a node. So I'm just going to say map zip/node. Okay. So now I have a sequence of all the nodes, I believe. But let's actually go further and see if that's true. Um, oh, well, we haven't actually written the converter that converts it back into, because this is like a shorthand form for this. But I think this is the same thing, right? Actually, and since we're doing the nodes, um, do we want to just do this ourselves or what? I mean, well, no. I mean, what's the purpose here? The purpose is to get the list of depths. So a sequence of a sequence of depths is what we want here. Um, if we do the next thing, we're going to do a depth first search. So it's going to be in, iterated path order. And so we're going to need to reorder them. Actually, wait, you know what I'm doing is actually pretty dumb. We don't need the next at all. We just need to take the down and then all the rights, right? Let's see about that. I saw rights, I think. The right siblings of this lock. Oh, that's it, I think. Well, that's super easy. Plus, I think we can do this iteratively. Okay, well, kind of undo everything I just said, right? It's all cool, but we don't need it. I think we're just going to take the tree. We're going to make a zipper out of it. Then we're going to iterate down on the zipper, right? And then on each down, we're going to iterate across on each zipper. Well, really, they're locks at this point. They're not. I don't know what you call these. I'm going to call them Z's. But when you iterate down, you're just going to say. So how do you know when you're done going down? I hope it returns something obvious. Or nil if there are no children. Okay. Wait, does this work? No, because it's not the case that it would work on any. What is it called? On any complete binary tree, because your leftmost node should be your lowest node, but there's no guarantee that this is going to be a complete binary tree. So we actually, I guess, do need to run through every permutation, because like it's possible that the leftmost node is actually the depth of the right node is lower than the depth of the left node, right? So wait, but we don't care about left or right. But you could get stuck in what is kind of like a local minima, right? Um, yeah, if you always just going down the first leftmost child, right? If you're always just going down the leftmost child, it's possible that having gone just down the leftmost child, you're not at the longest, at the greatest depth, basically. So I don't think this does work. It would this approach of always going down the first child, would work on a perfect binary tree. Um, a complete, jeez, dude, a complete binary tree, but it will not work on a just completely generic tree, binary or otherwise. Um, so I think we do need to just. I think the safest thing to do is to run across every single node, right? Um, I say that. Well, no, because I need to know what your lowest node is, honestly. I need to know in order to because I was thinking, well, I could actually I mean, I was thinking go down to the left side on the complete binary tree, and then just ask for all the nodes to your right, include yourself, and that's the nodes at every level, right? But actually, I mean, and I was thinking, what if you could ask for all the nodes to your left and your right? So you basically include all the nodes to your left, yourself, and all the nodes to your right, and that's definitely all the nodes that are your siblings at that level, right? But then I thought, well, but then I need to know the path that gets me all the way to the lowest level node. I need to know that path, unless I go in and I actually just insert nodes at every level until the only node that's been inserted at this level is my own self-inserted node, right? So we could write it that way. We could say, hey, I'm going to give you a zipper, and so then we could do the down thing, where basically you give me a tree, and what I'm going to do is I'm going to go down the leftmost node every single time. And if there is no leftmost node, I'm going to insert a new child that is leftmost node that I can identify as being a node that I've inserted that wasn't part of the original tree, right? And I'm going to keep going down that thing. And the thing that's going to terminate me is when I go down that node and I discover that I am the only node at that I as the inserted node am the only node at that level, right? When that happens, I know that I should terminate myself. I should actually not include myself, right? So that's how you could do it, and I think that has some elegance, honestly. Um, actually, I'm curious whether lefts and rights are those lazy sequences. Um, is there a siblings for that matter? No. Yeah, and I don't think these are lazy. That'd be kind of cool if you could, and if down's not lazy, right? No. But if all of these were lazy, then you can actually just you just return a thing that actually costs nothing, but that's basically going to go. Yeah, how would down be lazy? Anyhow, all right, let's do it. Let's try to do it the way we're going to try to do it, which is we're just going to go through every single node, um, and and we're going to take every single item all the way to the end. I think that's what we have here, right? It looks rightish to me so far. It's not quite converted into the format. I guess let's do that next. So this needs to actually end up being, or we need to get either, or we need to convert this into that, which I guess just means converting a sequence of maps with IDs into um, uh, nodes to, let's just say maps to back. Yeah. So what this guy's going to do is very simple. He's going to take a sequence of maps, and he's just going to basically call. Actually, I think literally all he's doing is calling map on the ID of X and S, right? And he's calling map V on the ID of X and S. No, that doesn't matter. Map V on the ID of X and S. We got the ID, and now we're gonna put a vector. Screw it, that's just stupid. Just do it as one thing. Okay, we still have valid code there, but now we need to just kind of convert them into... I think these may not be easy to diagnose though, so we may need to put them, to remove them. Oh. Alright, but we did the wrong one. Oh, and it's actually going to be a grouping, isn't it? What is it? See, I don't like this because now I can't see what it actually is returning. So what about just no, why are we getting ID of 1 and nil now? What's going on there? Because we haven't done the zip node. Maybe. We've taken the tree. We've converted it into a zipper. Okay. We can't really do that yet. I think we just need to get all of them, because then we're going to need to order them by their size. But we're not. We're going to need to group them. Is there a way to just get their height? I guess that's the path, right? So, yeah, if we group them by their tree, whoops, no, by their, whatever they are, we get their zip slash path, and we take the count of that, right? If we group them by that, then we should have a map now that contains a bunch of keys and values. And right, group by responsive map, right? I think so. A function and a collection. Yeah, and returns a map. Okay. So we group by the map. And okay, that's cool. Let's just see what we see. Yeah, so now we got a map with 0 and this. And I want to apply just... I mean, I guess if we just map it, right? Again. We just map it. it will take a collection of a key and a value, right? Which is really a sequence. And we can map that into a key and a sequence where we've mapped the zip node of every item in that sequence, right? Okay. I don't really need the node even. I need the well, it's okay. I mean, I got the node, yeah. And now I want to put it back into a well, I want to do, there's no guarantee of order here, right? It happened to pick 0 because there was only 0 elements, but there's no guarantee of order. So we want to kind of undo the map in key order. That sucks. I don't know how to do that. I guess we can probably just use sorted map, right? Wait a minute. I don't think I've hardly ever used this thing. Turns a new sorted map with supplied map. If any keys are equal, they are handled as if by repeated use of assoc. So if we do this, now actually I think, well, this is interesting. I've never done this. This is cool. Whoops. But if we into a sorted map, yeah, you can just do that, of course. Right? Now our keys are in a sequential order, right? And they're already grouped by, so we don't need to group them, right? And I think now if we just take the seek on that, well, let's see what we got actually at this point. Still something that looks just like a map of with keys as the keys and values as a sequence. But then if we actually seek on, or no, we take the vowels of that, right? The vowels will also be in key in sorted order, right? So that looks like maybe something. And I don't know. Let's try. Let's just try. I'm going to put this in here for now, which I don't entirely agree with, but I don't want to map cat, but I want to plot. I want to map on each grouping. So I guess I sort of want to map on the maps. I don't know. This is looking stupid, but okay. What about this one? So rather than returning 1, 2, it just returned 1. Lame. Alright, so let's back it up and see where it went wrong. Alright, we had children, an ID, yeah. So it only had one element. It doesn't seem to have had 2 elements, which is weird. So it's almost like all locks isn't working. Yeah, it's still the case that all locks has not worked the way we want it to work. Oh, wait a second. It shouldn't be zip in. You should be taking while predicate is not zip end, right? So I think it should be the complement of zip in. Okay, hard to read. I'm gonna. You somehow had 2 1s. That's interesting. And then 1 2. Well, that's a complete failure. All right. How did that happen? did that happen? Two ones and then a 2. Okay, great. Alright, let's just see. I'm just going to start writing my own little functions just for this in here. This takes all locks, which is, or this is a zipper at this location, and it's going to take the zip/node, and it's going to take the ID. Let's just start the zip/node. So I see 1, 2, 3. Is that what I see? 1 with ID 1, 1 with ID 2, and 1 with ID 1 again. Oh, I went back to my original. Oh, because I started at the original. Oh, so we really... Oh my gosh, we don't have to do any of this. Son of a gun. I don't think we need to do this at all, because we're going to start at 1. So we have 1 already. We don't need to end at 1 and take 1. Son of a gun. Alright, waste of time. Yeah, so that's an infinite sequence, and that makes sense. So we do, but I think we just really just need to take while you're not at the end, right? It's not a magical take while, it's just a normal take while. I think we've infinitely, there we go. So. What did I get out of that? I got... That doesn't look right at all. But that's because we're not taking the complement, we're taking... Okay. So yeah, we start with... The first one we got was 1, and the second one we got is 2. Is ID 2. Which is the guy in here. Okay, cool. Alright, then we're gonna just... Let's see what happens, actually. Not good, but... Oh, well, we did do this. Not bad. That's a bit embarrassing. We didn't need to do that at all. We already have the root node. It's the thing we built the tree out of, or the zipper out of. Now, however, if you did run through a whole lot of stuff, right? And made a whole lot of changes. I guess if you made a bunch of changes in the tree as you traversed it, right, as you went through zip next, then in our case, our end is identical to our beginning. But if you made a bunch of changes and then you're at your zip end, after doing the very last change on the zip end, then you would probably be able to detect that you're at the zip end, and you could just go up to the root elements and then ask for the node of that, and all the changes would be applied. So I guess there's not really a need for this take while plus 1. I can't think right now why you would need, I mean, at least for the zipper, why you would need to say take while and the thing that I failed on, right? Take while this predicate is true plus the thing that I failed the predicate on, But really, that's what split with does for you anyway. So you could, whatever you need to do, just do it this way and figure it out. I think this makes sense in that yeah. Anyway, I don't think we need it. Alright, let's see what else we got. Let's see if the other two still pass. Oops. See if this one passes. That's great. Let's try for 2. Be aggressive. Try for one of the more complicated ones. Okay. Alright, well, so I'm pretty comfortable with that then. There may be things I missed, but it actually... Let's see if there's... I mean, if we can sort of... I mean, I kind of want to leave this here just because it might be useful. Didn't end up using this. Yeah, where's it called? Oh, yeah, well, we didn't test it yet. Or we need to test it. So I guess we did end up using it in the sense that we used it for the test. So, but that's fine. Let's just put it right here. And okay, yeah. So what was complicated about this? Well, building the zipper was not complicated, right? You just had to, I mean, just literally consider what the structure of the tree is, or of each node in the tree is, and that's it. Yeah. And it's weird. It's weird actually to use the different terminologies because, like, do I use the word node here? I really shouldn't. I feel. Well, in the problem description. No, so we use the terminology node too, but a node is a segment of the tree, I guess. Yeah, or is a. I mean, a tree and a node are the same thing, so maybe we shouldn't use the word tree. Is what we really shouldn't use. Maybe we should just call this node to zipper, right? This takes a node and returns a zipper. And then we run through all locations in the zipper as a sequence. Then we group them by their the size of their path, you know. Then we map each of the key values with the key here, and the value, all we're doing is just converting each of the items to their, I guess if we want to, let's make it into nodes, right? And then we're going to put that in a sorted map. Then we're just going to, because the sorted map now will do things in incrementing order, we can now just take the values and get them in order. That is their path size order. Then we can map on that to just get the IDs. Which I don't think this is really part. I would not consider this what the function should do, actually. But I think we should just do that at the end as part of the expected versus actual. Right. Very bad. Oh, it doesn't make any. Oh, I'm on the completely wrong problem. Oh, I did it. Okay, so it's control minus. Oh, I hate how this stupid thing does this. All right. but we're okay. So we're back to here. I'm gonna do this. Yep. Gonna do that. And oops. On the first one, it's actually failing. Oh, yeah, you don't have an ID anymore, do you? Now it does. Now it's fine. I don't care about that, honestly. Okay, I think that's that, right? It returns a sequence of an in order sequence of all the items at that path, including like the linked list, right? Okay, cool. Yes. Well, actually, let's look at the hints. So 107, 123, and 135. 107. Try modifying a graph search outcome to track the depth from the root. Huh? Okay. 123 is a hash table or array that maps from level number to nodes at that level might also be useful. And 135 is you should be able to come up with an algorithm involving both depth first search and breadth first search. So our algorithm is actually, well, it's really kind of, I mean, it's a depth first search walk through the tree. But is there not a thing to just give me a sequence of the entire tree now that I think about it? That seems a little hard to believe, doesn't it? Like next is to like just to give me all the elements in the tree. Oh, I bet you this is it. Returns a zipper for nested sequences, given a root sequence. Don't know exactly what that means. Oh, this is a type of zipper. Nope, I guess there's no like thing, but I guess it's not hard to build. We built it right here, basically. But yeah, there's no default, just give me a sequence of every node in the tree. I guess that's actually probably what walk is for, right? I mean, walk can walk pretty much any data structure. I think is this thing that's, and you know, it would like if we did walk, and we're walking across, and we're getting a sequence of things. We'd have to like write little predicates about like, well, I guess the only predicate we'd have to say is the only thing I want to modify is children, right? Because we want to kind of skip over walking. I'm never clear the actual sequence that's returned from the map, which is the two element vectors, right? The key value pairs, and also the individual values like the keywords and the ID number and the vector. We only want to walk. We only want to modify the. We'd only want to modify the things when they're maps. Everything else we just ignore. So I guess that would. Well, we don't. In this case, we don't want to modify anything. But we don't. We could have written it with closure walk, probably just used an atom at the top, right? Like create an atom at the top, closure walk the entire thing for every map, you know, um, sort of for everything that is a map, add it to the list of nodes. Now we have a list of nodes, right? Every single node in the node, you know, in the root node from the root node downward. But then for each node, we need to sort of process it, and I think that would basically just be a matter of finding the deepest child, which is kind of sucks actually as an algorithm, right? Because now you have a list of nodes, and for each node, you need to basically look at its children and ask what is the deepest level child. No, that's actually not. That's not what you want. You want the opposite. You want to know how many people are above me, um, and that's not possible with a node, right? At that point, you don't know it. So maybe closure walk isn't a good solution. Um, so I don't know. I think our solution is okay, and that's it. Yeah, this is really not necessary. I don't know. Maybe you should take out things you don't use, even though I think it was interesting to discover it. Um, I think that's kind of like, I think I'll leave it because I think that's kind of like the purpose of having video is if somebody's actually curious, they can look at the video and figure out why was I doing this? What was I thinking? You know, um, and otherwise they can just be like, you know, whatever. Uh, let's which cool all box. It's a pretty short solution, right? I mean, it's just oh, this isn't part of it at all. This is also not part of it. This just is part of testing, isn't it? Wait, did we use this at all? No. Okay. I think we just ended up inlining that right there. So we really don't need that one. And then, yeah, I mean, the whole solution just ends up being a few lines, which is actually pretty good, I think. Let's see, 10 to, or 22 lines. That's a pretty good solution for a... And yeah, the other thing we could have done is use this BNF thing, or BFS thing that we built over here, right? But then all we'd have to have done is convert the tree into convert the node that we have, the tree that we have, the binary tree we have, into a graph, right? Which it is, but just convert it into the format the graph expects, which is basically just a map of I forgot actually what this was. I think this is I should have written down what the data structure actually looks like. This is a map of vertices to vertices, right? Their connection. I don't know exactly what this was for. Graph. Um, were we actually using the graph in a real way, or were we just passing it around for no reason? Well, we're definitely using it. When graph contains a vertex, okay, then we walk through it. We're also keeping track of this visited thing. Graph is not changing through time, though. What is a vertex in this case? Oh, it's the starting vertex. Wow, that should have been better labeled, honestly. You should call that starting vertex, I think. Okay. Partially the confusion on that one was I can never remember what the plural vertex is. So I was like, vertex, does that mean a thing or a collection of things? It's vertices, I think. Um, all right. Anyway, that was list of depths. That's problem 4.2 of, or 4.3, I should say, of Cracking a Coding Interview, 6th edition. Cool. That was good. We were able to finish it pretty quickly, I think. And yeah, that's definitely it for today. See y'all tomorrow. We'll be doing problem 3 in the chapters. Hopefully, I mean, this is assuming I can finish all of them, right? Uh, 4 on chapters 4, which is graphs or trees and graphs. Chapter 8, which is recursion and dynamic programming. Chapter 10, which is sorting and searching, and chapter 16, which is mono problems, and 17, which is hard problems. So that'll be tomorrow. Yeah. Alrighty. So let's do. Oh, looks like we've already started. Oops, no, we haven't. All right, chapter 4, problem 3. That is list of depths. I remember this one. Or I remember reading the description on this one. Lips of depth. See, I'll show you. All right, let's get ourselves actually using this one. And okay, I'll read the question. Given a binary tree, design an algorithm which creates a linked list of all the nodes at each depth. E.g., if you have a tree with depth D, you'll have D linked list. Okay, so effectively they're kind of saying, like, in their language, you might return an array of linked list, um, or maybe a list of list. I don't, or linked list of linked list, whatever, right? So just for a graph, return, or for a tree, I should say, return a list of lists. Now, actually, a while ago, we built, I think in 4.1, problem 1, we built actually this BFS thing, right, which can take a graph, right, and actually returns a lazy sequence of all the nodes in breadth first search order for that graph. So if we actually did convert the tree into a graph, which is pretty trivial, right, and is always possible, then we could actually use this to basically just get the lazy sequence and then just partition by the size of the list, right? Where the first item will be you, right? The item of length 1. The second item will be all your direct children. The third item will, or the third grouping would then be, I said item, but I meant groupings. The third groupings would be your grandchildren, and so on and so forth. And that would actually be pretty cool. But we haven't yet actually used. Oh, that's right. And I was going to look at. I forgot. Yeah. We haven't used ClojureZip yet. So what do we want to do? Do we want to just convert it into a graph and then just use the BFS we've already written? Or do we want to actually pull a ClojureZip in so that we can actually walk over a graph? Hmm. Let's try to just use closure.zip, even though I think the graph solution is kind of cool. I guess it doesn't. I don't think it makes a difference which way you do, because with the graph solution, right? Obviously, to walk across the entire tree is a linear operation, and to build the graph data structure that represents the tree data structure, um, is also a linear operation because all you're doing is walking across the entire tree and sort of adding the nodes into a data structure that has, rather than representing the tree just as nodes directly referencing other nodes, you represent it as a data structure where you have actual nodes and or edges of vertices, right? But it's the same thing fundamentally. So, um, okay. But let's just try to bring vertex in. That's going to be a bit of a challenge, not for any good reason, but just because I actually don't know how to. Well, actually, let's just see if I can do this. Maybe closure zip is just already there. Uh, it's been several years since I used closure zip. 5 years ago, I was using it a whole lot. Um, 'Let's see if it likes that. Ah, that's too bad. They should include this. There's no reason not to include this. Yeah, well, okay, so it's not that easy. So, all right, this is gonna kind of diverge from actually solving the problem, but let's just make sure there's no simple example of doing this. If you don't find it here, it's probably not there. Okay. So maybe I'll add this as an issue, is can we just get closure zip? Just read through these to see. Okay, well, anyway, so I don't think we have closure zip by default, which is too bad, but um, I'm actually kind of surprised closure.zip isn't included. We got XML and CSV. I'm surprised that these don't actually use closure.zip underneath. Well, it's XML I meant, not CSV. Yep. Uh, okay, so we're looking for. Alright, we could try doing this. I've never done this. Is this how we do this? I'm not clear. Where does closure zip really hang out? So it's. Just out of sanity check, let's just check this. Okay. Um. Not really quite clear how to include this because it is closure core that I'm. Or it's closure, not core, but closure. It's just. It's just the normal closure that I'm using here, you know. Uh, so how do I include closure.zip if I can't reach it for some reason? Not sure. But it seems like they're just referring to shell. But he says specifically I've added in shell. Hmm. Okay, so here's how I add in my own class path, I think. How do I add in? Okay, let's see what happens here. Not really clear. And then I need to find something that's like this. I don't know. I guess closure.zip. I'm just not clear what we're doing here, honestly. I mean, a depth should. This is clearly a entire GitHub project, not a small thing from within Clojure core. Or God, I keep saying that. Clojure, you know. So how do I just add in closure.zip? Let me go look on. I should really. I mean, I'm logged in right now, so I won't. But I should really go on, see if there's a Babashka group, or not group, but Slack group. I just asked that question. Babashka. Am I spelling it correctly? There's definitely a Babashka group. Okay. Alright, well, you join it then. What the heck is going on with the browser? It's like this thing's like hung or something. What the heck? This is weird. I can't join a channel. What's going on? Oh, there's a stupid little button to the right. I can't just double click it. That's dumb. You gotta click this join button. Okay. There's really nothing in closure.zip that is. I don't even think it's changed in years. Let's see. Yeah, 2010. Like, the zip is really old. So I'm just gonna ask on the Babashka Clojurians channel. How do I? Sorry, I gotta write some stuff on other things. Sorry, this is pretty lame, but I also have my Mac to my left, and I have my Linux computer that I'm working on. But the keyboard is just so different on both of them, including like the fact that the Mac has like certain keys. Like my key repeat rate is set to something insane on the Mac, but it's different. Like I ended up making just a huge number of typo errors as I type. Um, all right, so I asked the question, and let's see if I can just figure it out myself. So I mean, I don't know if we can just include our self or something. Right? I mean, like this isn't what I'm really requiring. It's just closure core. Um, oh, I keep saying that, but I'm just requiring closure, which I assume is already kind of included at some level, and so I don't know whether I should include it twice or require it directly and then require closure.zip from closure. Uh, latest Babeshka. Oh, and so the Michael Borkent, the guy who made I'm looking at his picture. Yeah, it's the same guy. Yeah, the guy who made Babashka. He says it's part of the latest BB. So I think we may just need to upgrade our and by BB I mean Babashka. So I think we may just need to upgrade Babashka. So let's see what my current version is. BB Babashka 0.091. All right. So there's no mention of it. No, I don't think they've yet updated their thinger. But that's fine. So I guess this is a project.clj. And where's the version number? Oh, it's calculated. Okay, how do I figure out what the current version is then? I read it from resources, Babashka version, it looks like. Babashka version. So yeah, there is something slightly newer. How do I upgrade to Babashka? Oh, okay. Now this may ask for a password, in which case I will log out for just a second so I can enter my password. That's evidently not how I installed Babashka. I think I installed it, yeah, I just installed it directly like that, so I guess I upgrade by just, oh, I think I installed it like this. Okay, well, I'll be back in a second as I upgrade.